AP Calc 3.5 day number 1. Prior to getting into 3.5 day number 1, just wanted to look at a few derivative rules, review those. The constant rule, the derivative of a constant is 0. The power rule, the derivative of x to the nth is nx to the n minus 1. The constant multiple rule, I was calling it the linear rule before, but the derivative of c times f of x is c times f prime of x. The sum rule, as we've seen, and the derivative of e to the x. Those are a few of the rules. We'll see a couple more on the next slide. Okay, as you can see here, we've also got the product rule. We did that plenty of times in the last lesson or two, as well as the quotient rule, as well as this little saying here, low d high, so that's the denominator times the derivative of the high function, or the numerator, minus numerator times the derivative of the denominator over the denominator squared. Here's the extended power rule. Really, honestly, it's not any different than the power rule, other than it can be extended to just the integer values or other values, like, for example, x to the 1/2 power. So, and then the derivative of e to the kx, which is partially using what we've talked about prior, which is called the chain rule. You don't know about the chain rule yet, but you're about to. So, yeah, let's go ahead and get into 3.5 day number 1. Okay, 3.5 day number 1, derivatives of trig functions. We've already talked about this, but the derivative of sine, derivative of cosine, and then this thing called the jerk. The jerk is the third derivative. So the jerk is d cubed y dx cubed, or y triple prime. Many names for it, f triple prime, all that good stuff. Okay, a couple of important items to note when we start here is that the limit of sine x over x as x goes to 0 is 1, and the limit as x goes to 0 over 1 minus cosine x over x is 0. So in using those, we can evaluate a couple limits here, more just for the fun of it and for some repetition with limits. But let's use these properties to evaluate these limits. Okay, so what would then the sine of 4x over x equal? Well, I can make this, to some extent, look like sine of x over x by multiplying the top and the bottom by 4. So I'm really multiplying by 1. So what does that do? Well, I can bring the 4 in the denominator in. Right, so this would be then the limit as x approaches 0. I can bring this 4 inside the limit using properties of limits. Therefore, I would have sine of 4x over 4x. So let's do a quick substitution, right? So let's say that 4x equals u. So then the limit, oh wow, that says 0. How about 4x equals u? Oh, let me change it. It's not allowing me to erase it. Equals u. So then the limit as x approaches 0 of 4x should equal 0, right? So then that means that u should equal 0. So this would then be the limit as u approaches 0 of the sine of u over u. So it takes on the exact same form, right? Just with a different variable. So this would evaluate to 1. So 4 times 1 would, of course, be 4. Okay, I can do something very similar in this other example here. What I'm going to do is I'm going to multiply top and bottom by x, top and bottom by 3, and top and bottom by 5. Okay, and I'm going to show you how we can utilize that. Okay, so now this limit would equal the limit as x approaches 0 of, let's keep this 3/5 right here, and bring in the 3x from the denominator, as well as bring in the 5x from the numerator. Okay, so now what you'll see is very similarly to what we had over in example 1. I've got 3/5 times the limit as x approaches 0 of sine of 3x over 3x times 5x over sine of 5x. Therefore, using the product property, this is equivalent to the limit as x approaches 0 of sine of 3x over 3x times the limit as x approaches 0 of 5x over sine x. All right, now, with that being said, this will equal 1, and this will equal 1. All right, because if the limit is sine x over x approaches as x approaches 0 is 1, then the limit as x approaches 0 of x over sine x will also be 1, right? 1 is reciprocated and still equal to itself. Therefore, I get 3/5 times 1, which happens to be 3/5. Okay, a little bit of limit work there for those of you who may not remember. Okay, so without using your graphing calculator, let's sketch a period of sine on the same axis. Let's also sketch the derivative of sine and see what it looks like. So here's the function sine x, max of 1. All right, it maxes out at pi over 2. It's 0 at pi. Has a minimum value at 3 pi over 2, and then comes back to 0 when x equals 2 pi. Okay, so let's identify where the derivative, okay, so this is f of x equals sine x. And we're going to graph f prime of x and try to hypothesize what that function might be, although you may already know it. Okay, so what would the slope be here at pi over 2 of sine x? Well, it's going to be 0, and same thing here at 3 pi over 2, the slope will be 0. Therefore, the output of the derivative function will be 0 there. Now, also look here. What does the slope look like it might be close to? Well, I know it's negative. Let's just guess a -1. That looks like about -1. And the slopes at each of these points, if the function were to continue, right, as it would to the left of 0, it looks like a slope of 1, and that looks kind of like a slope of 1. So what does this graph look like it's shaping up to be? Well, it's shaping up to be cosine x. So the derivative of f of x equals sine x is cosine x. Okay, so let's go over the questions that they've got here. When the sine function is increasing, what is true about the derivative? Well, when sine is increasing, its derivative is positive. When sine is decreasing, its derivative, or its derivative function, is less than 0. You can see that that holds true for the entirety of that graph. When the sine function is decreasing, its derivative is less than 0. When the sine function reaches a max or a min, what is the value of the derivative? We went over that. They would be 0 at those max values. So now we know that the derivative of sine of x is cosine of x. Let's look at the next slide. Okay, as we mentioned on the last slide, we're not going to use our graphing calculator, but you could. Okay, so we could type into y1 sine x, and then type into y2, excuse me, not into y2. Yeah, we could, into y2. I want you to type in, press math 8. Math 8, and what it'll do is it will give you notation like this. It'll ask you to fill in some boxes, right? In here, I want you to put an x, and in here, I want you to put y1. All right, and then when you graph it, you'll see sine x show up, and then you'll see y2 show up, which will be cosine of x. Okay, you can do that on your own. That's cool. So the derivative of cosine x, and we're not going to go through the details of it, but if f of x equals cosine x, by details I mean I'm not going to sketch all that stuff right now, its derivative is negative sine x. You can do that on your own. That's a little bit of fun. Okay, so what is the derivative of tangent x? Well, tangent x is really sine of x over cosine of x. So what would happen if I took the derivative of sine x over cosine x? Well, I'd use the quotient rule. So that would be the low function times the derivative of the upper function. Derivative of sine x is cosine x, so I get cosine squared, minus the upper function times the derivative of the lower function, which is negative sine x. So I get minus a negative sine squared x, okay, over the lower function squared. All right, so remember the identity from back in the day, cosine squared plus sine squared? Well, that equals 1. Therefore, the derivative of tangent x, oops, let's get brackets there, is 1 over cosine squared x. Well, that means that the derivative, if I wanted to put it in terms, simpler terms, of tangent x is secant squared x. Okay, what is the derivative of cosecant x? Prove it using the derivatives of sine and cosine. Okay, so let's look at cosecant. All right, so cosecant is equivalent to 1 over the sine of x. So if I took the derivative of that using the quotient rule, that'd be low d high. So the low function, sine x, times the derivative of the upper, which would be 0, minus upper times the derivative of the lower, okay, which is cosine x over sine squared. Okay, so the derivative then of cosecant x would equal negative cosine x over sine squared x. Now I want to simplify that into, instead of a rational function, I want to write it as the product of two functions. So the derivative of cosecant x would be the same as negative cosine x over sine x times 1 over sine x. So this is cosecant, this is negative cotangent, so the derivative of cosecant is negative cosecant x, cotangent x. All right, let's look at the trig rules chart. Derivative of sine x, cosine x. Derivative of cosine x, negative sine x. Derivative of tangent, secant squared x. Derivative of cosecant is negative cosecant x tangent, cotangent x. Derivative of secant is secant x tangent x. And derivative of cotangent x is negative cosecant squared x. All right, notice any function that starts with a c, its derivative has the opposite sign. Okay, the rest of them, sign stays the same. All right, we got 2 more slides. Let's get to them. All right, I see y double prime of 3 pi over 2. So y prime of x is the derivative of sine x, which is cosine x. Y double prime of x will equal negative sine x, right? I'm just taking the derivative of the first derivative. Therefore, y double prime at 3 pi over 2 is going to equal negative sine of 3 pi over 2. Well, the sine of 3 pi over 2 is negative 1. So y double prime at 3 pi over 2 will be positive 1. Okay, it looks like we're going to have a calculator allowed question here. Find the equations of the tangent line and normal line to the graph of that thing at x equals pi over 4. Okay, so first I need a point. So I'm going to do that actually manually here. I'm going to find a point. And that point is going to have the x value pi over 4. And it's going to have the y value of whatever y of pi over 4 is, which will be cosine of pi over 4 over pi over 4 squared. Gross. That's going to be kind of nasty. So that's 1 over root 2 over pi squared over 16. Let me see what that would be. 1 over root 2 over pi squared over 16. That would be the same as 16 over pi squared root 2. That's pretty disgusting. we'll go with it. Pi squared root 2. Okay, there's my point. Now I need my slope. So I need to know y prime at pi over 4. So what I want you to do is I want you in y1 to enter cosine x over x squared. Okay, enter that into y1. I'm going to do the same right now. Okay, just a heads up, always have your calculator in radian mode when you're doing this. Okay, I want you to press math 8. Okay, and then in this, you're going to have d over d space, parentheses, and then a vertical line, and then you're going to have a box which will fill in with x once you type it in, equals, and then you got this like dotted space here. Okay, so what I want you to do is I want you to type in x here, and then automatically it'll fill an x there. I want you to type in pi over 4 here, and then in here I want you to press alpha, trace, and insert y1 right there. Okay, so an x, and alpha trace y1, and a pi over 4. All right, I get, my answer comes out to be, I'm going to round it to 3 decimal places, negative 4.065. Okay, therefore, the equation of the tangent line, okay, tangent line will be y minus 16 over pi squared root 2 is equal to negative 4.065 x minus pi over 4. All right, and the normal line will be y minus 16 over pi squared root 2. And I'm going to take 1 divided by my answer and make it the opposite sign. So I get 0.246 x minus pi over 4. This value here that we came up with by hand, 16 over pi squared root 2, I'm assuming they would allow you to use your calculator since it's calculator allowed and have a decimal value there. So just heads up. Okay, example 4. Let's work with this one. Ooh, we got a limit, and this is the limit definition of the derivative. This is f prime at pi. Can you see it? Can you dig it? Right? This is f of x plus h minus f of x all over h. So what is f of x? F of x is equal to tangent x. I'm evaluating at x equals pi, so I want f prime at pi. Instead of doing all the work to find that limit, which you don't even know how to do yet, I want you to find the derivative. First, let's find f prime at x, which will be secant squared x, and then I want you to plug a pi in. Now, secant squared of pi may not be easy for you to recall, but the cosine of pi, I bet you know. Okay, the cosine of pi ends up being negative 1. Therefore, the secant of pi will be the reciprocal of negative 1, which is negative 1. So secant squared of pi will be negative 1 squared. Therefore, f prime at pi will equal positive 1. Answer is E. All right, let's keep going. Example 5. If the line tangent to the graph of f at point 28 passes through the point negative 1, negative 1, then what is f prime at 2? Okay, so we've got a point, and our point is 2, 8. We need a slope. Well, that slope, we don't have a function, but we do know 2 points that the function goes through, right? The tangent line goes through both of those points, so the slope will just be 8 minus a negative 1 over 2 minus a negative 1. Therefore, f prime at 2 is equal to this slope. That slope ends up being 9 over 3, which equals 3. That was a nice one. All right, we got one more slide. Let's do it. All right, number 5. For how many values of x will the lines tangent to the graph of y equals 4 sine x and y equals x squared over 2 be parallel? So we want to know where their slopes are the same. That means that I want to know where y prime, let's call it y1. y1 prime is equal to y2 prime. Let's call that y2. So I want to know where 4 cosine of x is equal to 2x over 2. So where is 4 cosine of x equal to x? Okay, so my suggestions on this are to graph the two. I'm going to graph 4 cosine x, and I'm going to graph x. I'm going to use my calculator, and I'm going to go in a window where my max value is 5 for y, my min value is -5. I'm actually going to go out to -5 and +5 as well here. So what you're going to see is you're going to have cosine maxing out at 4, and then based on my calculator, I'm having the graph for cosine that ends up looking kind of like that. Okay, and then I see that when I graph y equals x, it looks as if those graphs intersect at 3 points. Okay, it doesn't say calculator aloud, but I'm going to say calculator aloud. All right, number 6, last one for the day. What is the instantaneous rate of change of the function f at x equals 0, given that f equals that thing? Okay, so I'm going to take the derivative because I'm looking for f prime at 0. Okay, that's my goal. So what is f prime at any x? Well, again, quotient rule. So we're going to take low times the derivative of the high. Derivative of the high function or upper function is secant x tangent x minus high d low, which is 1, all over x plus 1 quantity squared. Okay, so I'm going to have 0 substituted in for all values, and therefore I get 0 plus 1, which is 1, secant of 0, which is 1, tangent of 0, which is 0. Okay, now I don't like the way this is working out, so scratch that. I'm going to move this stuff over. So f prime at 0 is 0 plus 1 times secant of 0 times tangent of 0 minus secant of 0 over 0 plus 1 quantity squared. Okay, so let's talk about this. This will be 1. The secant of 0 is interesting. That's the reciprocal of the cosine of 0. Cosine of 0 is 1, therefore the secant of 0 is also 1. The tangent of 0, however, is 0. So f prime at 0 will equal 1 times 0 minus the secant of 0, which is 1, all over 1 squared, which is 1. Therefore, f prime at 0, or the instantaneous rate of change of f at x equals 0, will equal -1 over 1, which is -1. All right, there you have it, guys. That is 3.5. We'll see you in the next video.